So, in this video, we're going to talk about arrays. Now, these are very important to a ray tracer. The name kind of gives that away. So the first thing is, what is array? So array is a bit like a vector with a position. So I said earlier that a vector is just an arrow, a direction, and we can draw it wherever we like on the coordinate grid, and it's still the same vector. But array, this point matters. And this is a starting point for that ray. It's not a vector anymore, but it does still have a direction. So the simplest way to represent this is store the start point and store the direction. And that's exactly how we're going to do it. And a key thing to point out here is that this ray doesn't have to end here. This ray can keep going on. It can go on infinitely. Depending on the context, the size of the vector might matter. It might not. Generally, when we consider rays, we're going to only consider rays with where the size of the direction vector is 1. Because, as you will see later, this then makes all of the equations a lot neater when we care about how far away something is from that start point. And so, let's start talking about how we're going to find these points of intersection. So to do that, we're going to need a nice way of representing points on an array. And so the way we do that, we're going to write a mathsy equation. So we're going to say r hat is a point on the ray. And P is the start of the ray. So that's a point in space, and it's the starting point of the ray. It's this point here. D is the direction. So all of these things at the moment are vectors. Now I'm going to leave space here for one more thing, and then this is our equation. So any point on the ray can be written as P plus TD. So the question here is, what is T? So T is like distance. So P and D, the start and the direction, they both describe the ray, but T doesn't. T, you can think of T as describing a particular point on the ray, rather than the ray as a whole. So T is not a vector, it's just a number. So if you think about, say, if T is 2, that's sort of saying go a distance of 2 along the ray from the start, and that's where R is, the point you're looking for. If T is 1, it's go distance 1 along the ray, and that's your point R. So by varying the value of T, we can get any point on the ray. Now, usually we'll only want to consider positive values of T, because light rays only go in one direction. They don't go backwards, so anything behind us, where T is a negative, we don't care about. And we'll usually want to discard those values, but sometimes they might be useful. So, now we can describe a ray in 3D space. If we want to see where it hits anything, we need to be able to describe those objects as well. So the next object I want to talk about is a plane. Now, this is not an aeroplane, but instead, and this is quite hard to draw, but it's a big piece of paper. So this piece of paper is so big that it doesn't have edges. It keeps going on. It goes on forever in all directions. It's an infinite piece of paper, except it's perfectly flat, which most pieces of paper aren't. So it's hard to draw this. You're going to have to come up with a bit of imagination, but a particularly useful place for planes is for representing the ground, because it's not always, but it can be very flat and it should be very, very big. And so to describe a plane, we're going to use a reference point. So you can pick your favourite point on the plane. It doesn't matter where. I'm going to pick this one here. And we're going to call this P. So this is our point on the plane. And now, with only a single direction, we can represent the entire plane along with this point. So we're going to call this direction n. And that's because n is the normal of the plane. So if you haven't come across normals before, that means that n is at 90 degrees at right angles to the plane. Now what's neat about this is that once you have this normal, the whole plane is uniquely defined by this normal and a single point on the plane. Because wherever I move this normal, it's still at 90 degrees to the plane. And so that's sort of how we describe it. The plane has to be flat, or we'd have to move the normal as we move around the plane, and we don't want to do that. So that's how we get a big flat surface. And then to create a nice equation, so we're going to use r again to represent a point on the plane. But this time we're not going to set r equal to something. What we're going to do is say, well, r minus p dot n equals 0. And yes, it seems like I'm plucking this out of thin air, which in a way I am. But a way to think about this is if I pick a point r on the plane, and I'm going to draw the line from P to R. So this vector that goes from P to R, this is represented by R minus P. Okay, so if you don't believe that R minus P is the vector from P to R, let's draw a little diagram. So here we have the origin, so this is 0. Here we have P, and here we have R. So what we can do, as we described vector addition in the previous episode, well, we can say P plus, let's just say this vector is x. So P plus x equals R. And so, with a little bit of rearranging, we get x is equal to r minus p. So that is where we get this r minus p coming from. So the key thing is, this r minus p is a vector that lies flat on the plane. And that means it must be at 90 degrees to the normal, because the plane is flat. And, as we mentioned in the previous episode, if you take the dot product of two vectors that are at right angles to each other, you will always get 0. So this equation does in fact describe the plane in terms of a reference point and the normal. So what's nice is now we have a ray equation, which is r equals p plus dt, and a plane equation, which is r minus p dot n equals 0. And so if we want to find a point that is on the ray and the plane, so this is a point where the ray hits the plane. So if we're interested in where our light ray hits an object, this is the point we care about. This is where they hit each other. And if we can find the value of t, then we know how far the ray has to go to hit the plane. So, all we need to do is say these two r hats are the same thing. Now, you have to be careful with this one because these two p's are not the same thing. That's supposed to be a not equal sign at a funny angle. It doesn't look great. I apologize. But But the key thing here is because these two r's are the same thing, we can just plug this and move it down into here. Now that drawing's getting a bit messy, so let's just write out. So this is P, but this is the point for the ray, plus dt, minus the point on the plane. So I'm going to represent these two P's by P subscript R and P subscript P, so we can tell them apart, because they are different P's. And this dot n is equal to 0. So all I've done is take the equation for the ray and move it in to the point for the equation of a plane. So now we want to solve this equation to find t. And this is very similar to normal algebra with just numbers, which is very nice actually. So the first thing we're going to do is say that the dot product behaves a bit like multiplication, in that we can sort of multiply out the brackets. If you don't believe this, it shouldn't be too hard to verify using one of the definitions for the dot product from the previous episode on vectors. So I would recommend go back and do that if you're not confident this works. But if we allow ourselves to do that, we then get PR dot n plus, and note I'm putting dt in brackets here because dt is a vector, but t is not, so we cannot dot product t with anything else. So I want to make it kind of clear that we're talking about two different operations here. We're talking about multiplying by a number and dot product. They're two very different things, and we shouldn't confuse them. And then finally, minus pp dot n equals 0. So we're going to move the p's, that's a dot, we're going to move both the p's away onto the other side, so we don't have to worry about what they're doing when we want to get our t on its own. It makes it a bit simpler to look at. So this is another thing I'm just going to claim about how the dot product behaves, but again, it's not too hard to verify using the definition of the dot product, and that's that we can just pull this t out outside of d dot n. And then this is still equal to our thing with the p's. And now, this is really nice. So what we want to notice here is that this whole thing is a number. It's not a vector, because the dot product gives you a number, so we're getting two numbers subtracting. It's just a number. This bit here is just a number, and t is just a number. So this is just a nice simple equation. We don't need to worry about the vectors to get t on its own now, because it's all numbers, so we can just t is going to equal 1 over this dot product times this expression in the p's. Now, the only time we have to be careful is if d dot n is equal to 0. That is, if they're at right angles to each other. That is the direction of the ray and the normal of the plane. Now, the only time this will happen is if the ray is sort of going parallel to the plane. So usually this means they don't intersect ever. The only exception being if the starting point for the ray is also on the plane, and then the entire ray is within the plane. So if d dot n is 0, then either they don't meet, or every point on the ray is a possible meeting point. So that's a special case we'll have to consider separately, but in general, this equation will tell us how far we need to go along the ray to get to the plane. Now, this equation doesn't seem too intuitive, but we can think about it a bit like this. So if this bit here, it kind of sort of how far the ray starts. So we're finding the distance between a point on the plane and our starting point. So this is so if the ray starts further away, this will be bigger. If it starts closer, this will be smaller. And this sort of is how quickly we get there. So if it's at a very shallow angle, then d.n will be small, it will be close to 0. But if this is steep, then this will be quite close to 1. And we'll get in to the plane quicker. That's one way of thinking about it, but we needn't worry too much about what any of this means. We should just be able to type it into our code and get the result we want. So we're now going to think about another shape, the sphere. So the sphere is a bit more complicated, but it would be really boring if all we could put in our world was big flat surfaces. A sphere, it's round, it's going to make it easier to test other things in future because it's very predictable in a way, but it's not predictable to the extent of being uninteresting in the way that a plane is. And we're actually going to use a neat little trick that means we only need to consider a very special type of sphere. So we are only going to think about spheres. I'm drawing this in 2D, by the way, with circles, but the same thing sort of applies in 3D, where we're going to be working. So we're only going to think about spheres or circles where their center is here, the origin. So it sounds like cheating, but if we wanted our sphere to be somewhere else, so I'm going to draw this all in 2D, but if our circle or sphere is up here, and our ray is, say, on the side here, but we only have the equations to think about a sphere that's on the origin, well, the solution to this is don't use that coordinate grid, and instead move the entire coordinate system so that the origin is in the middle of the sphere. So that is a trick that we are going to be using, and it means the equation for finding where a ray hits a sphere is going to be a lot simpler, which is good because it's not the neatest looking equation. But it also means that for this equation, all we need to store is the radius. Now, bear in mind that when we store a sphere, we do also need to store its center point, because we're going to need that to move the coordinate grid. Without knowing where it is, we can't move the coordinate grid appropriately. So we do still need to store the center point. But for this equation, we assume it starts in the middle, and we're going to call the radius r. Now, I'm sure you've seen this before, but the equation of a sphere is just the size of any point is equal to r. And now this seems a bit funny because we're talking about this point as having a size, but all it means is the distance from the center point, the origin, to that particular point in space. And so, like before, with the plane, we can just plug the ray equation into it. And we get p plus dt equals r. And now we want to find t. Well, one useful fact we're going to use is that for any vector, the length of that vector is equal to the square root of that vector dotted with itself. You should be able to verify this from the definitions, like all of the other random facts I've pulled out of thin air in this episode. So do that if you're not confident with this, but this is how we tackle this problem. So if we say this is the square root of p plus dt dot p plus dt, we can now use the things we know about multiplying out the dot product to get rid of, or at least get most of this away from the t that we want to get out. But first we want to get rid of the square root, because that's really, really horrible to work with. So let's just get rid of it and square r. Now we have to be careful when we square both sides, because we might introduce extra solutions. The thing is, we don't need to worry about that here, because everything is nice and positive. Distances are always positive, so we know that square root exists. So we're not introducing or like overlooking the fact that something doesn't exist. That's fine. And r should also be positive, so that's fine. We needn't worry. And now when we multiply out this dot product, it's going to look a little messy, but we get p dotted with itself plus t squared times d dot with itself plus 2 times t times p dot d, and that is equal to r squared. Now notice here we have p dot p and d dot d, and we've already, up here, we've sort of discussed what that is. So this is the length of p squared plus t squared times the length of d squared. I just think it's a little neater to write it like that. But it also, if you saw the previous code episode, you'll notice that we have a function to calculate the square of the length. So that's going to be really neat to put into the code. Much neater than writing it dotted with itself. At least in my mind. But feel free to do it how you want. And if I just rewrite this a little, so we get t squared times the length of d squared plus 2t times p dot d plus the length of p squared minus r squared. This is all equal to 0. And this is a quadratic equation in t. And I'm not going to go into detail on how we solve a quadratic equation, as I'm sure you've seen this before. But the coefficients we get, which I will write out, a is d squared, b is 2p dot d, and c is the size of p squared minus r squared. So if we calculate these three numbers, it's just a normal quadratic equation which we can solve. And now quadratic equations don't always have solutions. Sometimes it has 2, sometimes it has 1, sometimes it doesn't have any. But if you think about it, with our sphere, we can have 0 solutions if our ray goes like this. We could have 1 solution if it just touches the edge. Or we could have 2 if it goes through and comes out the other side. So actually this is exactly what we should expect. And the number of solutions to the quadratic equation will actually tell us exactly how many places this ray passes through the sphere. And it gives us the positions of all those points, if there are any, which is really convenient, because it means that's not something we have to think about separately. It's just something we do have to consider in code, so we don't try to do anything silly like square root a negative number or divide by 0. In this episode we've talked about what rays are, we can find where they hit a plane, and we can find where they hit a sphere, if they hit a sphere. And we can find these distances. So that means if we just test it against all of our objects in the scene, we can find out where the first one is, which is really important, because that's the only one we're interested in. And also, if you want to think about your own objects, hopefully you'll be able to apply these techniques. If you come up with the equation for it, then put the ray equation in, and then you get the points of intersection. Now, as you get more complex objects, this can get a lot harder. And so, instead of getting our artists to come up with mathematical equations to describe the objects they want to draw, instead we're going to build it out of lots of little triangles. And while I'm not going to go into detail on how we do that now, I will say that we're going to need to make extensive use of our plane calculation for that. And that's something we will discuss more in a future video. I encourage you to think about how you would do it before then. But in the next video, we are going to go over the code for storing rays, planes, and spheres, and finding intersection points between them. So I look forward to seeing you then. Goodbye, and thanks for watching.